Hi everyone, my name's Owen Boberg and I was a postdoc at the University of Washington working with Lynn Jones and Jelko Avesic, and my goal in the project was kind of producing a lot of the runs that you saw in the call for white papers, running math, producing those outputs, and producing kind of the comparisons that we've seen. And I've also been heavily involved in kind of the development of the LSST Optim scheduler, and improving some of the tools that we have in math. And I was asked today to give a presentation that would kind of serve as a very basic tutorial of math. I understand that throughout the rest of this conference there'll be some hands-on workshops, where you'll actually get to run some code using Docker containers, which is a great way to do that because everyone has a working version of the code that's you can all kind of go through the notebooks, and that's kind of the best way to really dive into math and start to use it and change it the way that you'd like to see it to get the best science out of it. Before I get going, I'd first like to say thanks to Sarah for inviting me to give this talk. I'm very sorry that I can't actually be there in person or give this talk in person, and then I'm having to record it, but hopefully this still serves as a good tutorial for everyone who's at the workshop, and people will benefit for it. So before we start getting into it, what I would like to show is this it's a rather large list, sorry about that, of useful links. I just put this at the beginning so people can come back and find it easily without having to go through the entire slide deck. There's a number of good things that you might be interested in looking at here. We have an installation page, there's a math help page. There's also this list of available metrics. So, something that a lot of people might be interested in is, oh, I would like to measure this very specific thing for my science. Before you start writing your own code, it might be worth looking through all those metric lists and looking at all the different options that you have when you're running these metrics, because something could already exist to do what you'd like to do, you just have to set it up correctly. And so that page there, this metric list.html, has a very nice kind of breakdown of everything that's there, and you can look at all the different options you can set. There's also there's a nice set of tutorial notebooks, and then there's two places you should really look in the SimsMath contrib repository. There's this tutorials, and then there's the science and the transients notebooks. In the transients notebooks, there's a lot of interesting cases there where you're doing things like looking at a specific location on the sky and kind of looking at the light curve that would come out of that, and that kind of helps you drill down on the cadence. And so a lot of people are kind of interested in getting that out. There's, of course, the GitHub repository for math. There's my personal Docker Hub repository, and then at the very bottom there are these two links that I give to results web pages. And so this first one has all of the math output that we created for the white paper runs. And so you'll see there's these web pages that have kind of everything that you'd want to know about the runs. We run this huge batch of metrics on them, and so that's great for that. And the second link is it has a table of all these runs that we did, and it also has some very basic comparisons of the various runs to the baseline. So that's kind of good places to look to get a very large overview of everything that we produced, and it's probably a good place to start before you start or looking at for inspiration for your white papers that you'd be writing, to kind of see what we already produced and some of how those new simulations have performed, and how would you like to maybe see those change to kind of do the best science that you'd like to see. So the very first thing that we probably would like to just get out of the way, some people might be very familiar with math already, but we might as well, start at the top. So math is this, it stands for Metric Analysis Framework. I should have defined that at the very beginning, but it's this Python framework for understanding how telescope scheduling affects survey performance. And so it's developed to give you a way to directly interact with the output from an operations simulator, OpSim, survey. So that's something like the baseline 2018A database. And so this kind of gives you the tools to connect to that. It comes with a huge number of built-in metrics. All the metrics are these Python classes. You do have to know a bit about Python coding and a Python class and an object in order to write new metrics, but there is a nice tutorial notebook that goes over that already. It's called Writing a New Metric, and it's in the tutorial notebooks repository. And what we use this for is to take the output of OpSim, you run it through math, and then you can see if it's met all the science requirements that are defined in the science requirements document. That's a huge thing. And if you'd like to see the original paper for this by Lynn Jones et al., I give a link for it there. So like I said, this math is designed to work with OpSim databases, And so what is an OPSIM database? It's the results of running OPSIM, and it's a SQLite database. And what you get from that is this kind of, if you were to actually open up, baseline 2018A in using SQLite, and then you were to look at all the tables, you'd see this large list of tables. And MAF can access all of these if you'd like to do, look into them and see what's going on. But the one you'll probably use most often is summary all props. And and what I'll show next is kind of all of the columns that are within summary all props. And it'll look like anything you'd kind of think you'd be tracking when you're, simulating what a telescope is doing. So here I give the summary all props. These are all the columns. This presentation will be available, so you can come back to this. And you might notice that there's some columns that you'd expect to be there that aren't. Things like the hour angle, if you look through this list, they're not there, or this normalized air mass. But MAF has these things built into it called stackers, and what a stacker does is it will go and it'll take everything that it needs to calculate something like air mass, it'll take all the columns that it needs to calculate something like hour angle, and it will add that onto it if you're running a metric that needs to use the hour angle. So you can look at the stackers tutorial in the notebooks, and you can write your own as well. That's another easy thing to do. And so again, you can come back to this if you kind of have a metric in mind, but you're not sure if there's the information there that you need. So again, thinking about this idea of what is MAF, a lot of people's first interaction with it is these websites. You see this website, if you go to this link here, you'll see this kind of thing, and you have all these graphs and plots and numbers and maps, but this is just one tool in MAF. It's just something that you can do it's an easy way to display all the contents that are in a directory. So just keep in mind, this is not actually what MAF is, this is just one tool. And so now we're going to start getting into what MAF actually is doing. So at this very high level summary, right, I said you have this OPSIM database, and it kind of gives you that connection to the OPSIM database. That's something you always have to do. The next thing that it allows you to do, it allows you to use a SQL query to kind of choose the very specific data that you'd like to use. You can look at all of it at once, but if you'd like to do very specific things, you can use almost the same SQL queries that you'd use if you were using any kind of database. And then after you have the database queried, then you slice the data into groups. So this is similar to a pandas group by or any other kind of group by that you would do. And so then you would have your groups, these data slices. And once you have your data slices, then you go through and you calculate metrics on those data slices. And we'll come back to this, and I'll show two different ways of how this is going on, and so hopefully I can illustrate kind of the workflow that you need to have in your mind when you're thinking of what MAF is doing. So the next thing I kind of want to touch base on are this idea of a slicer. There are three main slicers that are built into MAF. You have this unislicer, which is very kind of simple. It'll just go all the way down the index of a database. So you'll just go all down, and you can do very simple statistics based on that, or you can bin things how you'd like. So you could do things like count the total number of visits. Another very simple one, but it's very powerful, is this 1D slicer. And what that does is it will group visits into subset based on some value that's in the OPSIM database. For example, if you go back to the summary all props, there's something called night. So you could use a 1D slicer to group things by night, for example, and then so you'd do the SQL constraint, slim down your data that way, and then you would do the slicer to slice it up by night, and then you would calculate some metric on a by night basis. And so that's another way of thinking about this. And I'm going to really kind of highlight an example, a couple different ways using the 1D slicer, just because it's easy to present in this kind of format with just a PowerPoint presentation. Excuse me. And this last slicer, which is also extremely important, is the heel pick slicer. And what that does is that it will take positions on the sky and it will map them onto heel pixels. And so that'll allow you to look at things like the co-added depth at a given portion of the sky, the average air mass for a given portion of the sky, position on the sky. And so that again is also very useful. And again, you can go to the slicer tutorial to get information on that. Okay, so now that we've kind of hit the big keywords that all kind of go into MAF, right? We have this idea of the OPSIM database, the SQL constraint, the slicer, and finally, the metric. I'm going to kind of show two different ways of looking at this, and we'll look at some of what the actual MAF code looks like, as well as what I'll describe as kind of MAF pseudocode-ish. And what I do is I kind of show you a database as it walks through these things, a very simple one that I've created. So hopefully this will, provide a nice illustration for both people who are brand new to using MAF or people who are very familiar with it but who might have not thought about it in this way before, and hopefully it'll make it a more powerful tool for them. So here's where I kind of lay out these ideas of these building blocks of MAF. Again, this is using the actual Python names of the objects that you'll see in MAF a lot. If you open up any of the tutorial notebooks, you have this idea of a metric bundle. That's very important to keep in your head. You'll see that a lot anytime you're running MAF. And what goes into a metric bundle is you have a metric. In this example here, I have this count metric, and it'll depend on the observation start MJD. Again, that's just a column that was in that summary all props table, which is in the OPSIM database. Sorry, there's a lot of jargon here, but I think it's good to hear it kind of in context. And then we have this slicer. In this case, it would be a heel pick slicer. Nside 64 is just setting the resolution of that heel pick slicer. And then you have a SQL constraint. And so in this case, it would just be grabbing only the R filter. And so I purposely put a cyan box around those because all of those things go together, a metric, a slicer, and a SQL constraint, to become a metric bundle. And that's exactly how you'd see it if you were actually writing the Python code. And the next thing that we have is this opsdb connection. That's how you connect. This is the object that you create in MAF, the Python object, and it's just a connection to the OPSIM database. And so we'll eventually see how you bring these two together in a metric, what's called a metric bundle group, and that's what eventually allows you to actually run the metric and calculate things. But before we get into that, what I would like to do is just follow a sample database through some MAF pseudocode. And so, but I wanted to show this first so you kind of have the real, Pythonic way of looking at things before we kind of look at the pseudocode. So again, what we're going to do is we're going to look at a database that I created. It's semi-fake, but I used a baseline 2018A to produce this example, and I'll show you the link where you can go and look at this and see exactly how I generated it. Okay, so let's go ahead and get started with this. Since I'm doing this for recording, it's hard to get any feedback if people are following me. Hopefully you are still, and you haven't fallen asleep, and this is still interesting. So here we go. This is what we're going to consider our OPSIM database. And what I did to create this, you can see there's a link at the bottom. There, it's just in my own repository, and it's just an IPython notebook. And what I did to create this is I just went through and I grabbed the first two observations for the first 7 nights of baseline 2018A. And the reason I did this is because, if I just grab the first 10 observations on a given night or anything, I just wanted to have a mix of days and filters just so I could actually highlight some things. Because, there's a lot of times where you're in kind of one filter for a very long period of time. So I wanted to make something that actually be interesting and allow me to highlight what's going on in MAF. So again, this is our starting point, what we're looking at. We can imagine we just have this week-long survey, and these are the filters that we got to, and we got these positions. And of course, something I would like to highlight, this still has all of the columns that I showed before, but just so it would fit on a slide, and so it wouldn't be too terrible to look at all the numbers, I just kind of used this one small subset, because I'm going to show some example metrics based on what we have here. So, again, keeping in mind what I was showing you before with the SQL constraint and the metric and the slicer, we're going to kind of walk through each one of those steps using this database. So let's go ahead and get into that. So the first thing that we would like to do is we just have a SQL constraint to only grab the data that you want. Of course, you don't have to do this. Anytime you're running a metric, you can do things with all of the data. You don't actually have to use a SQL constraint. There are some metrics where it won't really make sense. For example, if you're doing a co-added depth metric, you usually want to know that for a specific filter, you don't want to combine filters, but we won't go into that. So for example, in this one, I'm saying, okay, I'll just take the Z data, right? I just want the Z filter. So what I've done here is I've taken the previous, database that we're working with, and I've just highlighted the observations that were actually done in the Z filter. So again, you can see this is very simple, but you could do all sorts of interesting things with SQL constraints. You can do things like grab very specific date ranges. You can actually use this to get very specific proposals. So let's say you just wanted to measure something in the wide, fast, deep area or in the deep drilling fields. It's these SQL constraints that would allow you to do that. But for this case, I wanted to highlight a very simple case of just grabbing the Z filter because, it's something where we can all kind of relate to right away. So again, we've got the Z filter. They've been highlighted and blocked off. So let's go ahead and look at that. So What I've done now is we just have those observations from our original database that were in Z. Pretty simple, right? And so there's nothing that exciting in this slide. I was just showing you that we've gone from this whole big thing, and now we've just taken these 3 cyan blocks, and we've gotten this database. Great. So we've gotten through the first step. The next thing that we'd like to do is start to do the slicers, because remember, this is how we're going to start to group the data, and then finally we're going to calculate our metrics. So again, this is just a repeat of my previous slide, but I wanted to highlight that we're really going to just be looking at this 1D slicer, just because it's more interesting to look at in terms of an example than a unislicer, and it's a little bit easier to actually illustrate than a heel pick slicer. And so what we're going to look at here is looking at calculate the maximum value of a column on a per night basis is the example that I'd like to walk through with everyone here. And again, you can look at the slicers tutorial notebooks to get more information about this and see kind of how to use these to produce the science that you'd like to see. So this is, again, we've already applied a SQL constraint to the database, so you can see we just have the Z data. Great. The next thing that we're going to do is apply a slicer to this data that's already gone through the SQL constraint. And so at the very top of this slide, I give an example of how you would actually call this slicer. It's this slicers.1D slicer, and then you give it the column name. In this case, I'd like to slice on night, and then you can give it a bin size. Here, I set the bin size to 1. So what this means is that I'm going to take this database and group it by night, essentially. But you could do different bin sizes. You could do group bins of 2, 10. It just kind of gives you that thing. And I could have chosen any one of these other columns to kind of do that by, but binning by night gives a very nice example of, it's a nice way to illustrate it in a slide like this. So you can see each one of these data slices, as I'll be calling it soon, has been color coded. I don't actually know what these colors are. I just kind of, made them transparent so I wouldn't be able to tell you what one color is or another. But you can see each one is represented by a different color. And you've got your group 1, your group 2, and then there's night 4, night 5, and night 7. So let's go ahead and break those out into their own individual data slices. So this is kind of what MAF is doing under the hood. It's gone through the sequence constraint. Now we've applied this slicer, and that's grouping things. And once you've gone through this slicer, you get data slices. And that's what I'm illustrating here, right? You can really see that each one of these things has become its own data slice, right? We have night 1, night 2, night 4, night 5, and night 7. And the slice point, I'm saying these words, slice, data slice and slice point, because it's part of the MAF language or grammar. And so you have each data slice is just the data from that night, and the slice point is the night itself. So you can kind of, hopefully you're starting to see this picture in your head of how you're kind of paring things down into these different things to the point where you're actually going to calculate the metrics. Okay, so we've got these 5 different data slices, and now we're at to the point where we'd like to say, okay, now let's calculate a metric on them. And so for this, what we're going to do is we're just going to calculate, you're going to use the max metric. This is an actual metric with its in MAF. You can look at this link here, the first link, to see the code for how it's written and the parameters that it takes. But what it takes is it just takes a column name. So for this first example, what I'm showing is, let's say for some reason we wanted to know the maximum air mass. In the column that we're interested in is air mass, so we want to know the maximum value that's in a given data slice. So this is exactly what I'm showing here. We're going to set up the max metric. We're going to give it the column name air mass. And then what I'm only showing here is the first 2 data slices just because I couldn't fit all 5 on one slide. But you could imagine this going through each data slice. And what I'm showing here is the code of exactly what it would do. If you were to look at the code for the max metric, what it's going to do, it's going to just return the numpy maximum of the data slice given the column name. So in this case, it's just the maximum of the air mass column, which is, I'm kind of highlighting here, which in the case of night 1 is about 2.017. In the case of night 2, it's 1.421. And this is exactly what MAF is doing. If you'd like to see how this actually would go through in MAF, you can again look at this, the second link that I have here, and I show actually that if you calculate this with MAF, with like all the actual code, you get these same values. So I'm not just showing you some example that isn't correct. This is actually what MAF is doing. It's just a different way of presenting it that's hopefully simpler than just looking at the Python code. And what's really nice is once you have the data, the data has gone through the slicer, you can calculate multiple metrics on it. And so again, let's say you were also interested in something like the maximum 5 sigma depth. So all you would do is you'd set up a metric that has that column name, and you can see it's just returning the NumPy maximum of those different columns and those different data slices. It's really just that simple. So I really hope that this has kind of illustrated what this would do for each data slice. And then at the end of the day, when you set all this up to run through all your data slices, in this case, we've sliced things up by night, and we're going to look at the maximum value in some given column. You'd actually say, okay, run all these metrics on all the data slices and make me a pretty plot. So what's happening in that situation is this kind of exact thing. So this is what the metric data would look like at the end of the day. After you've gone through, you set everything up, and you run it, is you have a slice point. In this case, you have night 1, night 2, night 4, night 5, and night 7. And in this case, we ran a max metric, and the column that we were interested in was air mass, and returned these values. You can go back and look in the slides at what we started with, and you'll see that this is actually what they come out with. And then what MAF does, this isn't an actual MAF plot. This is still kind of something that I just made up within the slide, is that it would plot those exact things. You'd have a by night on the x-axis, and then you'd be plotting the max air mass in the z-band, remember, because that was the SQL constraint that we applied at the very beginning, and this is what you would get. So I really hope that kind of walking through all of this, right, you started with this database, you applied a SQL constraint, you just got the z-band data, you took a 1D slicer, you said I would like to slice the data by night with a bin size of 1, that gets you down to 1, and then I'd like to, for each one of those groupings or data slices, I would like to calculate some metric. In this case, we looked at what it would be like to calculate the maximum value of a given column. And that's really all that's going on with MAF. Of course, this is a very simplified version, and there are more complicated ways of doing it, but at the heart and the meat of what's going on in any kind of MAF setup is this kind of very basic thing. So hopefully this has been helpful, and maybe has been a different way of looking at MAF and understanding what's going on. This is kind of how, when I first started using MAF, I had to break it down for myself to fully kind of understand how the data were moving through the Python code itself to, give me these numbers and these kind of plots. So I really hope that this has been useful in that sense. And we're not quite done yet. I'd also still like to show how easy it is, sorry, I have to get this to write your own metric. And hopefully, now that we've gone through that previous example, this will kind of, you'll have a little bit more of a strong basis on how you'd actually build up your own metric. And this example that we're showing here, you can go to this link that's at the bottom of the slide, and you can get this exact thing and see these exact numbers. So with MAF, it really takes advantage of the object-oriented nature of Python. And if you would like to write a new metric, you do have to write a new Python class. There's a writing a new metric notebook that kind of walks through some of this and kind of goes through the different Pythonic parts of it. But here we'll just kind of go over a very simple example. And so the example I would like to look at is, let's say we want to look at the ratio of 2 maximum values for some reason. Let's just pretend that was an interesting case. So this is kind of what you have to do when you're starting this. And again, look at that writing a new metric notebook, because it kind of does tell you some of the little Python details that are going on here. But what you have here is you just have this initialize, this init, which is part of a Python class, and that's where you set up things that you'd like the metric to actually do, or values that need to be set, the parameters that need to be there for you to run the metric you want to run. In this case, we need a column that's going to be the numerator and a column that's going to be the denominator, and that's all you really need to set up. And the next thing that you have to write is this run method, and don't worry about the fact that it says data slice and slice point. That's not something that you really have to worry about unless you're writing a more complicated metric. Again, this kind of all goes into Python inheritance and stuff, but what you just really have to work out here is, given how you set everything up in the initialize method, the very first part of this class, is what you'd like to do with that data. So in this case, right, I'm just going to take the maximum of the column that's a numerator, the maximum that's the column of the denominator, and divide them, and then you get a result. So this is kind of, and again, hopefully based on what we saw with the previous example of walking through, this is kind of starting to make sense, and you could figure out where this data slice is going to come from. So let's pretend this is the metric that we wrote, and we're interested in seeing what it would do. And again, I'm going to come back to this idea of looking at my very simple database that I made up. You can follow these things through the notebooks and see how this would actually work out. So what is this metric actually going to do? So again, we're looking here at just the very first night. Again, this is our data slice. The slice point is night 1, and we're going to run our new metric on it. And you can see I called it max over max metric. And remember, if you go back here, you can see how I set it up. You have to give it this call numer and call denom, and that's exactly what I'm setting up, in Python. The parameters I'm saying is that the call numerator is the 5 sigma depth, the call denominator is the air mass. So if you were to set this metric up and run it, all it's going to do is going to take the maximum of the column that's your numerator, or the maximum of the column that's a denominator, divide them, and give you a number. In this case, again, I just did this as an example to illustrate. I don't think you'd ever actually want to calculate the 5 sigma depth over the maximum air mass, but it was just an illustration that I'd like to do. And again, you'd probably want to write this code a little bit more robustly so you wouldn't get a number in the denominator that's 0. But anyways, this is exactly what it would do, and you can go to this notebook that's at the bottom here and actually see it in action within the full math framework, and using all the right Python calls. Okay, so now we've been talking about this in this kind of pseudocode-ish kind of way of looking at this synthetic database that I created out of a real database, but what would this actually look like if you were going to run it in MAF? And what are you going to run into when you're actually running the notebooks? And that's kind of what I'd like to show here. We're not going to go into the details of it, because if you're able to get the notebooks up and running in Docker, it's much more useful for you to go through and click and run the cells and be looking at things. But I just hope that the previous example that I showed you, the simplified version of actually following some tabular data through the different pieces, is helpful. And now you can actually kind of almost put a name to the face, or a face to the name, excuse me, when you're looking at some of these just Python calls. So what we're looking at here, again, I call these building blocks of MAF. You saw this at the beginning of the slide. And hopefully now some of these names have some meaning to you. And you can associate these different pieces with an actual physical tabular data source. So again, we have this metric bundle. In this case, we're going to be calculating end visits. The metric bundle has a metric, a slicer, and a SQL constraint. And then at the bottom of this, we have this OpsDB connection, right, which is this OpsSim database. And again, hopefully think back to what we just looked at, right, of this very simple table that you had. I used all of these pieces in a way, but we just didn't use these the Python calls. So you've got these two, and they are two different objects, right? And so what you do next when you're using MAF, and what you'll see is that you need to create a metric bundle group. And all the metric bundle group, all that's doing is that it's taking your metric bundle, which was, again, the metric bundle is this combination of a metric, a slicer, and a SQL constraint, and it's combining it with your OpsSim database. So this metric bundle group becomes a new object, and you can see here, I tried to make this as close to the Python that you'll see in the notebooks as possible, is that the metric bundle group is actually the metric bundle, excuse me, the naming is a bit difficult to keep right. It's just a dictionary where you give it the name of the key is the name of the metric that you'll be running, and then the value is the metric bundle itself, and then you connect it to a OpsSim database. And again, this is kind of everything that we were doing before with the simple tabular example that I was showing you, but these are the kind of what the actual Python calls are going to look like when you're running it in the notebooks. So you create this group, it's all connected, it's all good to go. And then what's happening under the scenes, or behind the scenes or under the hood, or whatever, I guess I probably shouldn't be using those colloquialisms, but what's going on next is once you have that group, it has two methods in it. It has a run all method, and what that's going to do, it's going to take your OpsSim database, it's going to apply your SQL constraint, it's going to then apply your slicer, and then it's going to actually calculate the metric on each one of those data slices, exactly like we saw in the previous example. And so that'll go through, it'll calculate all your metrics, and it saves it in a nice format that you can always go back to. That's a great thing about MAF as well that I should mention, is that it really makes it easy to recreate your work. Everything is saved in a nice way, how your slicers were set up, all that great stuff. So it does have a nice provenance to it that you can always trace back. You can always recreate the results that you're seeing. So it has this run all method that's kind of doing exactly, like I said, it was doing what we showed earlier in the plot. in the presentation, and then it has this plot all um, method as well, which all it's doing is it's going to take your metric data and then plot it. Very similar to the example that I was previously showing, right, with that very simple graph. So that is all that I have, and I really hope that this has kind of maybe hopefully given you a new way to think about math. And then, by following this table data through it in a very kind of simple terms, and then I really hope now that you can take those examples and connect it to the actual Python calls and really use math to, the best to the best of its ability to get the science or see or test the simulations to make sure they're getting the best science out of it. And have a look at the notebooks. That is one of the best ways to play around with things. And there's a lot there. Have a look at the metrics that are available. And there again, even sometimes I'll go start writing a new metric and then realize, oh, I just had to set a parameter in one of the metrics that's always there. So definitely have a look at those before you start trying to write a whole bunch of new code that could actually already exist. And I guess that's it for me. So again, I hope that this was useful, and thanks again to Sarah for inviting me to give this talk, and I'm sorry that I couldn't be there in person. Thanks.